I'll just wait one more minute for people to join. Alright, let's start with the live session for week 2. So, in this week, I'll be covering topics from week 2 and 3. So, in week 2, I'll be covering some elementary signals, right? And in week 3 I will be covering elementary signals and then properties of data systems. And then in week 3 I will be covering about linear time invariant systems, uh, and a subclass of them, uh, which are specified by the linear LCCDE equations, linear constant quotient difference equations, right? So for the first for a while I'll be talking about week 2, and then I'll talk about some elementary functions, and then I'll just go through the properties of them discrete time systems. So let's just start it with week 2. Right, so let me just get started. Okay, alright, so forgot to mention, so yeah, so this is Sai Dinesh, PMR of IIT, scholar from IIT Madras. I am the TA for digital signal processing course offered by Professor C.S. Ramalingam. I am a third year PhD scholar from IIT Madras from electrical engineering. So this week we'll be covering topics from week 2 and week 3 of digital signal processing course. I'll just turn off my camera so that I'll save some bandwidth. Right. So yeah, and then first, so elementary signals. So let's just start with the impulse signal. So impulse signal is important signal in a discrete time. Impulse response has 1 at n equal to 0, and then 0 for n not equal to 0. So this can if we wish to draw it, we can represent it like at 0 we have a 1, and then for every other values it is a 0, and this can be represented as sequence in this way. So this is a discrete time impulse signal. right? So discrete time impulse signal is a fundamental signal that we talk, and then it is a very important signal that we discuss, because later part of the course, we'll be talking about impulse response of a system. So as you will see later, that every signal, a discrete time signal, can be represented as a summation of shifted and scaled versions of the impulse signal. So when we talk about linear or time invariant systems, we will talk about the impulse response of a system. Impulse response of a system means that we give the this impulse signal as input to the system, and then we find the output output of the system. So that is known as the impulse response. So how the system responds to an impulse signal, right? So this is the impulse signal. And then second one would be the unit step. So yes, as someone has done, I'll just start from the beginning. So this is Sai Dinesh, PMRF scholar from IIT Madras. This week we'll be covering topics briefly from week 2, and then I'll go on with week 3. So in week 2 I'll be discussing about some elementary signals and properties of discrete time systems, and then later we'll move on to week 3, where in week 3 we'll be talking about linear time invariant systems, their properties, and the subclass of systems known as the LCCDE, which is the linear constant quotient difference equations, right? So as of right now, I started talking about the week briefly about the week 2, where I'm talking about the elementary signals. So first one is the impulse signal that we have. Yes, Tilak, this session is being recorded. Yeah, sure. The session is being recorded and will be uploaded to YouTube. Right. So first is the impulse signal that I'll be talking about. So impulse signal is the delta of n, represented by delta of n, and then which is equal to 1 at n equal to 0, and then 0 for n not equal to 0. As we can see, it is represented by the signal that we have here, and then in a sequence representation, this is the sequence. So impulse signal is a very important signal, because later part of the course we will see that any signal can be represented as a shifted and a scaled version of impulse, summation of shifted and scaled versions of the impulse signal, right? So and then when we talk about linear time invariant systems, we'll be talking about impulse response of a system. Impulse response of a system means that we give this particular impulse signal to a system, like delta of n, to a signal, and then we get the impulse response. So the response of the signal to an impulse signal is known as the impulse response. So that is the impulse signal. So next we move on to the unit step signal. So unit step signal here is represented as u of n equal to 1 for n greater than or equal to 0, and for n less than 0, right? So this has support of 0 to infinity. So again, unit step signal is also quite important and fundamental signal that we come across a lot during this course. And then as we can see, this unit step signal can also be represented using the sum of sum of shifted and scaled versions of the unit impulse signals. So this is the impulse signal, and then we talk about the unit step signal. So next we talk about causal and anti-causal signals. So causal signal means that x of n equal to 0 for n less than 0, right? So this is a causal signal for all n, so for n less than 0. So this is a causal signal. Causal signal is when a signal only exists in the positive time index. So and then next one is the anti-causal signal. for which x of n equal to 0 for n greater than or equal to 0. So this is the anti-causal signal. So example of a causal signal would be x of n equal to a power n for n greater than 0, and then 0 for n less greater than or equal to 0, and then less than 0 for mod a less than 1. So so giving this constant mod a less than 0 means that it will be an exponentially decreasing function, and then eventually it will be a absolutely summable sequence. So and then an example of anti-causal would be x of n for a power n less than or equal to 0, and 0 for n greater than 0. So this is an anti-causal signal, right? So this has a support of 0 to infinity, and this has support from minus infinity to 0. So these are the causal and anti-causal signals, right? Yes. So next, in the last class I've talked about complex exponentials, discrete time complex exponentials, real and sinusoid. So as we discussed in the previous class, just briefly revise from previous class, we see that complex exponential have a period of n. Complex exponentials are always 2 pi periodic. So I mean, not always a periodic. So for example, if we have a signal x of n which is cos omega naught n plus theta, which is a real signal, so this omega naught can simply be in the range of 0 and pi. So any value of omega naught can be brought to 0 and pi. And then second one would be x of n is equal to e power j omega naught n plus phi. So this signal belongs to the complex domain, right? So this here, in this case, omega naught belongs to minus pi and pi. So any value of omega can be brought back to minus pi and pi in the case of complex exponentials, right? So this is what we have discussed in the previous class. And then if we see like in the frequency domain, 0, pi, 2 pi, minus pi, minus 2 pi. So this range is the high frequency range, and then these two are the low frequency range, right? So and then omega naught plus 2 pi equal to omega naught plus 4 pi, so on. So this is for the low frequency and high frequency signals. So next we talk about the discrete time systems. So discrete time systems, so for the notation we will be using it as a signal x of n passed through a signal a system, and then we receive a signal y of n. So this is the input and this is the output. So this is a discrete time system that we have. So x of n and y of n are both discrete time. Okay, yeah, and then first we'll talk about the memoryless property of the system. Memoryless system. So if the output at any given time instant n depends only on the input at the same time instant. right? So examples would be y of n is equal to a times x of n, and or y of n is equal to uh, cos of n plus 10 times x of n. So all of these are actually depending on those exact same time instance. So here this is actually not the signal, this is the amplitude that is being gained, that is being added by the system. So this does not, so due to this we cannot say that it is not a memoryless system, so it is a memoryless system. And then causal system also means that the output in a given causal also means that output in a given time instance does not depend on future samples. Output at n does not depend on future samples. So this is the properties. So and then next we come for the two most important properties. So 1 second please. Why is this not turning on? All right. So let's talk about the linear time invariant systems first. Right. 1 second. So linear time invariant systems. So going about the same notation that we discussed before, x of n, t, and then y of n, right? So an linear system, the linearity property of the system means that if we have some x of n which produces of y1 of n, x1 of n produces y1 of n, and then we have x2 of n which produces y2 of n, then in that case x1 x1 of n plus x2 of n will produce y1 of n plus y2 of n. So this, if this is satisfied for all signals, so this is for all signals, if this is satisfied, y1 of n plus y2, this is known as the linearity. And then second one is homogeneity. So homogeneity is when if we have a signal x of n which produces a y of n, then any constant times alpha of x of n should produce a constant times y of n. So for any complex or real alpha, depending on the type of system that we are interested in. So systems that satisfy both A and B are called, so this is A and this is B. Systems that satisfy both A and B are known as linear time invariant signals. Systems time invariant systems. So this linear time invariant systems are actually like of very important, because many real-time systems that we have can be characterized using linear time invariant systems. And then linear time these LTI systems, so these are also known as LTI systems. So these LTI systems actually possess very nice properties which make it very easier to analyze the system, predict the output of the system, and also So this linearity and time invariance are actually a very big deal in the systems, with respect to systems, right? So an LTI system possesses the superposition property. Like if we can represent, so which is superposition is like when we have alpha x1 plus beta x2, it produces alpha y1 plus beta y2. So this is known as the superposition principle, right? So if the system, an LTI system, possesses the superposition property, so if we can represent the input as a combination of base, basic signals, which we see that which we see later that they can be represented as a linear scaled and shifted version of impulse signals. So if the input is represented as a linear combination of basic signals like the impulse signals, then the output of the system can also be characterized as a linear combination of the responses of the elementary signals like the impulse response. So this is a very desired property that we can say, like systems, LTI systems are very desirable, which make them very easy to analyze, right? So complete characterization of the LTI systems is done using a convolution sum, which we'll just get into it. So so like for example, so we see that if we have a signal x of n, for example, so and then x of minus 1 times delta of n plus 1 will give us x of minus 1 for n equal to minus 1 and 0 for n not equal to minus 1. So this basically gives a signal which is equal to the x of minus 1 at minus 1. So similarly, like x of 0 times delta of n is equal to x of 0 at n equal to 0 and 0 for n not equal to 0. So in this way, any signal x of n can be represented as a shifted and the scaled version of impulse response, of the impulse signals, sorry. So this is k n minus k, so x of k into delta of n minus k. So if we see that, so like x of 0 plus delta of n plus x of 1 delta of n minus 1, so on. So this is an shifted and scaled by these coefficients that we have here. So these are the coefficients that they are being scaled with. So any signal can be represented as a shifted and a scaled version of the of various impulse signals, right? So now if we consider an LTI system. Right, so if we have an LTI system, and then if we send a impulse signal delta of n, so that we get a signal x of h of n at the output, so this is known as the impulse response, right? So the response of a system to an impulse signal is known as the impulse response. So due to this superposition property, like for example, if we have alpha a times delta of n, this will give a times h of n. If we have b times delta of n minus 1, this will give b times h of n minus 1. All of this is because of LTI properties. So if we have a signal x of n which is represented as a shifted and scaled versions of simple signals, then what we get here is x of k h of n minus k, for k equal to minus infinity to infinity. So this is known as the convolution that we have. So y of k is y of n represented as x of k h of n minus k for k equal to minus infinity to infinity. So this is known as the convolution sum, and this is represented as x of n convolved with h of n. Sorry, it's okay. Yeah, so this is the convolution, right? So we can talk about like one or two examples, right? So let's say we have a signal. Example, consider an input x of n, which is alpha power n times u of n, and then h of n is u of n. So where u of n is unit step, right? So if we can draw the x of n that we have, what we have is it's like a decreasing magnitude. So that we have here x of n is alpha power n into u of n, but then again we have the h of n here, which is a unit step. So if h of n is u of n, or let k be the variable here, so h of k is u of k, then h of minus k is u of minus k, which implies h of n minus k is equal to u of n minus k. So if we write this, so this is the unit u of minus k, and then this is u of n minus k. So if it is shifted to the right when n is positive, and it is shifted to the left is if n is negative. So what we have here is, what we need to find is x of n, sorry, y of n is x of k h of n minus k for k equal to minus infinity to infinity. Like for example, if we have to, so this is, it is like you take the impulse response, reverse it, and then shift it to get n minus k, and shift it with respect to shift it by n samples if you want y of n. So for y of 0 you shift it by 0 samples. If for phi equal to 5, y of 5 you shift it by 5 samples to the right. So and then you multiply those x of k with h of n minus k, and then you sum up the solution, sum of the signal, that the resulting signal that you got. So that will give you the value of the output signal at that particular time instant y of n. So if we see here, this signal only exists on the right hand side, that is only on the positive side. So if we bring this h of n minus k to the left, that is when n is less than 0, there is no common area where they overlap. So then the resulting signal would be 0. So for n less than or equal to 0, y of 0 is 0. For n greater than or equal to 0, y of n will overlap from this 0 to n range only. So it will be like k equal to 0 to n alpha power k, which is 1 minus alpha power n plus 1 by 1 minus alpha for n greater than or equal to 0. But for n equal to 0 it is 0. Therefore finally we can write it as y of n is equal to 1 minus alpha power n plus 1 by 1 minus alpha times u of n, right? So this is the resulting signal that we have. So if you want to like plot this with respect to alpha, it will be like so it will be like gradually increasing to 1 by 1 minus alpha, right? So this is y of n that we have. So this is an example of the convolution, how we do convolution. So you take h of k, you reverse it, and then you shift it, and then you finally get the h of n minus k. Shift it by n samples when you need the output at y of n, output at the n sample. So reverse, shift, and multiply with x of k. That will give you y of n, right? Yes, so this is one example. So this is a case where both of them are infinitely existing, like have support of infinite support. So let's say we have a sequence which where both of them are finite, for example. So another example where this of n is 1 comma 0 for 0 less than n less than or equal to 4, and then 0 otherwise, then h of 0 equal to alpha power n comma 0 for 0 less than n less than 6 otherwise. So both of them are finite line signals that we have right now, right? So let's say like, so x of n is like 0 1 2 3 4 x of n, but y of n here, and then we consider alpha greater than 1 here, but since it is only a finite value, it is finite range, we have a finite signal, right? So this is of this form where it will start from 0 at 1, 5 6 0 1 2 3 4. So h of n. So finally what we need to do is y of n is equal to k equal to minus infinity to infinity x of n h of n minus k, right? So we split this. So how? So let's represent this as h of k. So k is the variable here, right? How do we get h of minus k? So h of minus k is the time reversed, which is equal to alpha power n, alpha power minus k for 0 less minus 6 less than or equal to n less than or equal to 0. So and then h of n minus k is again shifted version. So this will be of this form, where h of n minus k, right, it will be decreasing. This is n, it will be n minus 6. So this is h of n minus k. So this is existing only in the positive side. So if we have this h of n minus k for n less than 0, it will be entirely on the left side, which is in the negative side. In that case, there won't be any overlap, right? So let's write it as region 0. So for n less than or equal less than 0, there is no overlap, which implies y of n equal to 0 for n less than 0. Next we have region 1. So region 1 is, so this is entirely on the left side. Now we slowly move. So this is the signal, so we slowly move it to here. So like it starts going into the positive side. But then what is the length? The length here is 4. So we'll consider the case where for 0 less than n less than 4. So sorry, 0 less than equal to n less than or equal to 4. In this case, what we have is x of k h of n minus k is equal to alpha power n minus k for 0 less than or equal to k less than or equal to n, because below 0 to the left side of 0 there is no overlap at all. So 0 to k to n or 0, right? So finally y of n would be k equal to minus infinity to infinity, alpha per 0 to n alpha power n minus k. So this is a GP that we have here, right? So and then like for a finite summation, what we have is r equal to 0 to n alpha per r is equal to 1 minus alpha power n plus 1 by 1 minus alpha. This is for the GP progression that we have. So applied this here, what we get is y of n equal to x of k h of n minus k equal to alpha power, just rewrite it, k equal to 0 to n alpha power n minus k. So k is the variable here. So this is equal to sigma alpha power n into alpha power minus k. So since k is the variable here, we can bring it outside. So this will be alpha power n sigma k equal to 0 to n alpha power minus k, which is equal to alpha power n k equal to 0 to n alpha minus 1 power k. So for this we apply the GP progression that we have here, which will give alpha power n into 1 minus alpha minus 1 power 5 by 1 minus alpha power minus 1. Finally what we have is alpha power n minus 4 minus alpha power n plus 1 by 1 minus alpha. So finally what we have is, so if we solve the GP progression, this is what we get, which is y of n is equal to alpha power n minus 4 minus alpha power n plus 1 by 1 minus alpha for 0 less than n less than 4 less than or equal to 4, right? This is the interval, sorry, 1 second. So oh, sorry, this is for, I made a mistake, sorry. So for this k equal to 0 to n, what we have is y of n is equal to r equal to 0 to n alpha power r, which is 1 minus alpha power n plus 1 by 1 minus alpha. But what we have next is the region 3, where n greater than 4, but then n less than or equal to 6. So in this region we have an overlap again, but then we have a different range of overlap. So here we have this y of n. So here y of n is equal to k equal to 0 to 4 alpha power n minus k. That was my mistake. Now next we'll come to the region 4, where this signal, that this h of n that we have, starts going out of this region, like this is h of n minus k is this region, right? So this like starts going out, right? So for region 4 we have n greater than 6, but then n less than or equal to 10. In this region, x of k, h of n minus k is equal to alpha power n minus k comma 0 for n minus 6 less than or equal to k less than or equal to 4, right? This again is solved by k equal to n minus 6 to 4 alpha power n minus k, right? So if we say r is equal to k minus n plus 6, then we have y of n is equal to r equal to 0 to 10 minus n alpha power 6 minus r, which is equal to, again, alpha power 6. R is the dummy variable, alpha power 6 can be brought out. So alpha power 6, r equal to 0 to 10 minus n alpha inverse power r, which is equal to alpha power 6 1 minus alpha power n minus 11 by 1 minus alpha power minus 1, which is alpha power n minus 4 minus alpha power 7 by 1 minus alpha, right? So now the region 5 is where n is greater than 10. Again there is no overlap. So here y of n equal to 0 again. So finally what we have is y of n equal to 0 for n less than 0, 1 minus alpha power n plus 1 by 1 minus alpha for 0 less than n less than equal to 4 alpha power n minus 4 minus alpha power n plus 1 by 1 minus alpha for 4 less than n less than 6, and then alpha per n minus 4 minus alpha per 7 by 1 minus alpha for 6 less than n less than or equal to 10 and 0 for n greater than 10. So this is the final result that we have here. So this is y of n when x of n is convolved with h of n. This is the final result. Okay. So we can talk about one more example, or we can just move to the continuous. Let's just do a continuous time example. Right. So let me think about 2.8. Yeah. So let's just consider a continuous time example. Right. So in the continuous time case also, what we have is x of y of t is x of t convolved with h of t is equal to minus infinity to infinity x of tau h of t minus tau into d tau. Similar case, but now we have an integral in place of a summation because it is a continuous time signal. Right. So let's take an example. Maybe it will be clear with an example. So let's take x of t is equal to e power 2t into u of minus t, and then h of t is equal to u of t minus 3. That way, okay. So x of tau. So let's consider x of tau and h of t minus tau. So x of tau is of this form. So this is x of tau for tau, but then this right here is h of t minus tau, which is reversed. So again we have the same x of, we consider h of tau, we time reverse, we get at h of t minus tau, and then we shift it to t minus tau. So this is what we have here, which is a shifted unit impulse response, shifted and time reverse, which is t minus 3, and this is 1 0 0. Right. Okay, so this is t minus tau. So how do we do this integral that we have here? So which is y of t is integral minus infinity to infinity x of tau h of t minus tau d tau. Right. So for t minus 3 is less than 0, which implies t is less than or equal to t less than or equal to 3, we have an overlap from until that point of t. So y of t will be minus infinity to t minus 3 e power 2 tau d tau, which is equal to 1 by 2 power e power 2 into t minus 3. But for t minus 3 greater than or equal to 0, the summation is until 0 to infinity, because after once this goes to the right hand side, but then this is only till negative 0, sorry, only till 0. The overlap only becomes this part. So for t minus t greater than 0, what we have is y of t is equal to minus infinity to 0 e power 2 tau d tau, which is equal to 1 by 2. Right, so for t greater than 0 we have a constant, until then we have an exponential. So finally y of t is expressed as, like, it grows until 3 and then it becomes flat. So this is the convolution. Y of t is equal to x of t convolved with h of t, which is equal to minus infinity to infinity x of tau h of t minus tau d tau. Now for the next part, we'll talk about the properties of time invariant systems, right? Oh, sorry. Sorry. I hope the recording is working. So got disconnected. It was my fault. So now we'll talk about the properties of linear time invariant systems. So next, that will be the next topic. The properties of time invariant systems. So first one would be the commutative property. So properties of time invariant systems, linear time invariant systems, right? So first let's talk about the commutativity property. So the basic property in convolution in both continuous and discrete time is that it is a commutative operation. That is, in discrete time, if you consider x of n convolved with h of n is equal to h of n convolved with x of n, which is equal to h of k x of n minus k for k equal to that's infinity to infinity. So this is a commutative property. So this can actually be verified with by changing the variables in this one. Once we expand this in terms of convolution sum, we just need to apply the change of variables and then we end up with this formula. So the output of an LTI system with input xt and impulse response ht is identical to the output of an LTI system with input ht and impulse response xt, right? So that is the case of the commutativity property. So next we'll talk about distributive property. It's being recorded, right? Hello. Yeah, it's okay. The next is the distributivity property. So this is another basic property of convolution, where if we have a convolution of x of n with h1 of n and h2 of n, this is equal to convolution of x of n with h1 of n plus convolution of x of n with h2 of n. So and then the continuous time variant is x of t convolved with same. It's exactly the same, just with the change of variable. So x of t convolved with h of t plus x of t convolved with h2 of t. This is the convolution. So basically what it means is that if we have a system x of for which, if let's talk about discrete case only. So if we have a signal x of n which goes through a system which has both h1 of n and h2 of n, this gives y of n. This is equivalent to having a system x of t with h1 of n and h2 of n, which gives y of n. So this is what is basically known as the, this is what this represents. So when we have a system, a parallel system, then the output of the system, if the output of the system is summation from the parallel system, then it is equal to the output from a system which is a summation of all the impulse responses h1. So this is what distributivity implies, right? So let's see an example, right? So let's say we have x of n is equal to 1 by 2 power n into u of n plus 2 power n u of minus n, and then h of n is equal to u of n. So here again we have two parts for the system. So just like we wrote x of n convolved with h1 of n plus h2 of n equal to whatever we got, so the same is also true when x of n plus x2 of n when convolved with h of n gives x1 of n convolved with h of n plus x2 of n convolved with h of n. So basically if we have a signal, but then if we can represent that signal as a sum of basic signals again, and if we have an impulse response, so because just with for the LTI systems, it is equal to the convolution of each element, every individual part of the signal, and then summing up at the output. Both of them are same. So this problem can be tackled with this situation here. So we have is x1 of n plus x2 of n, where this is 1 by 2 power n into u of n and this is 2 power n u of minus n. So what we do is 1 by 2 power n into u of n, we give to h of n, we get something, and then we get 2 power minus n, and then again we give it to h of n, we get another, which is y1, and then y2, we get final output is y1 plus y2 of n, right? So I think we can like solve the we have the impulse response as well, h of n, so we just have to like basically do the, so this is convolution of 1 by 2 power n u of n convolved with u of n, and this is 2 power n u of minus n convolved with u of n. So then again we get the same output. So then we have the third property known as the associativity property. Where we have, so this is another important and useful property for communication, for convolution, which is associativity. So we have x of n convolved with h1 of n, again convolved with h2 of n. This is equal to x of n convolved with h of n convolved with h1, h2 of n. So and then again continuous time equivalent is x of t convolved with h1 of t convolved with h2 of t is equal to x of t convolved with h1 of t again convolved with h2 of t. So yes, so these are the three basic properties of LTI systems. So commutativity, distributivity, and associativity. So next we talk about LTI systems without memory. LTI systems without memory. So this means that the system is memoryless if the output at any time depends only on the value of the input at the same time. So which implies, so y of n depends only on x of n at n only. So this, which implies that h of n equal to 0 for n not equal to 0. So this is how the impulse response of an LTI system is characterized if it is memoryless. So like h of n is some constant times delta of n, right? So if this is true, then x of n convolved with h of n is x of n convolved with k times delta of n, which is equal to k times x of n. You know, if we simplest properties, if k equal to 1, then h of n is delta of 1, which is identity. This is one thing. So if a discrete time LTI system has an impulse response h of n that is identically 0 for n not equal to 0, then system has memory, right? So if h of n not equal to 0, h of n not equal to 0 for n not equal to 0, then it has memory. So next is invertibility. So invertibility means that if we have a signal x of t convolved with h of t impulse response, and we get a y of t, and again if there is another system h1 of t which produces a w of t is equal to y of t convolved with h1 of t, and if this equal to h of t, then h1 of t is the inverse of h of t. So if such h1 of t exists, if h1 of t exists for h of t, so this is an inverse system of h of t. So if we see this, so this is a intermediate output, so the system is this one. So basically if we have x of t going through h of t and then again convolving with h1 of t, if we get y of t which is equal to x of t, so when will this be equal to x of t? When h of t convolve with h1 of t is equal to delta of t, or discrete time case lo h of n convolved with h1 of n gives delta of n. Then in that case, this is known as the inverse. Right? Yes. So let's talk an example about inverse. Right? So let's say you have h of n is equal to u of n. So in that case, for any x of n which goes through h of n, y of n would be k equal to minus infinity to n x of k, which is an accumulator function that we have. Right? So this is an accumulator function. So what we desire is, so we have an h of n. What we desire is, what we want is h of n convolved with h1 of n should give delta of n, which implies u of n convolved with h1 of n should give delta of n. So yes, we were just talking about the inverse of an LTI system we have here. So invertibility, so we consider h of t as a system, right? And if we give an input x of t or x of n and h of n in the discrete time case, if we give x of n to h of n and we get output y of t, y of n or y of t, if this signal is again passed through another signal another system h1 of t and produces the same output x of t, then this h1 of t is known as the inverse of h of t. So if h1 of t is the inverse, then h1 of t is the inverse of h of t if h1 of t exists. So basically if we give x of t to a system with h of t convolved with h1 of t, it will give a y of t which is equal to x of t. Basically again the identity here. So this is the basic property that we have, h of t convolved with h1 of t is equal to delta of t. So here we are trying to solve a problem where h of n is equal to u of n. So we have h of n equal to u of n, which means that if we have a signal x of n which we pass through this h of n which is u of n, we get a signal summation k equal to minus infinity to n x of k, which is known as the accumulator. So basically it is summing up all the values of x of n until that point. So what we want is h of n convolved with h1 of n, which is delta of n, which is equal to u of n convolved with h1 of n equal to delta of n. Right? So if take h1 of n to be delta of n minus delta of n minus 1, in that case u of n convolved with, so basically we need to bring u of n to delta of n by like by through convolving it with some other function h1 of n. So u of n convolved with h1 of n should give delta of n. So if we consider this, which is delta of n minus delta of n minus 1, so this is equal to u of n convolved with delta of n minus u of n convolved with delta of n minus 1, which is u of n minus u of n minus 1, which is delta of n. So what we know is, if h of n is equal to delta of n minus delta of n minus 1, then u of n convolved with h1 of n gives delta of n. Therefore h1 of n is equal to delta of n minus delta of n minus 1 is the inverse of u of n. So yeah, and next would be the causality of the LTI system. So let's just take a break for a minute. So next we'll be talking about the causality of LTI systems. So causality of LTI system means so the output of a causal system depends only on the past and the present values of the input to the system. So if this is satisfied, then it is known as the causal system. So basically for a causal system, h of n equal to 0 for n less than 0. This is a causal system, right. So then next one would be the stability of LTI systems. So the system is stable if every bounded input produces a bounded output. So basically, if we have x of n, the magnitude of x of n to be less than b for all n, then the magnitude of the output y of n, which is magnitude of k equal to minus infinity to infinity x of k h of n minus k. So this is less than or equal to k equal to minus infinity to infinity h of k times h of x of n minus k. Right. So since this is bounded, for this to be bounded, we require k equal to minus infinity to infinity, this one less than infinity. So basically, if the system is absolutely summable, then the LTI system is Weber stable. This is the Weber stability conditions. Right. So sorry, I think I have shared my screen. So I'll just go through what I've done in the class just to summarize what we have seen until now, so that so first we started out with elementary signals. We first talked about the impulse signal x delta of n, which is 1 only at n equal to 0 and 0 for n not equal to 0. So this is the impulse signal, and as we have seen in the later part of this lecture, impulse signal is a very important signal which comes up everywhere, and then we talk about the impulse response of LTI systems and such. So next one is the unit step signal, where ufn equal to 1 for n greater than or equal to 0, for n 0 for n less than or equal to 0. And then we talked about causal and anti-causal signals, where causal signal means that x of n equal to 0 for n less than 0, right? So next we talked about systems. So we said that system is memoryless if the output of the system at a time instant n depends only on the input at that same time instant. And then we have so next we went to the linear time invariant system, where linearity means that if if x1 of n produces y1 of n and x2 of n produces y2 of n, we have x1 of n plus x2 of n gives y1 of n plus y2 of n. And then homogeneity means that if x of n produces y of n, some constant alpha times x of n produces some constant times the same constant times alpha y of n. Systems that satisfy both linearity and homogeneity are known as linear systems. Sorry, messed up here. So A and B are known as linear systems. But then we have another class. Sorry, I messed up. Yeah, we have another class of signals known as time invariant systems, where if x of n produces y of n, then x of n minus n naught, which is a delayed version of x of n, produces y of n minus n naught, which is the delayed version of the output by the same time. So so the system which is both linear, which is both both linear and time invariant is known as a linear time invariant system. So we have a times delta of n produces a of h of n. So if delta of n produces h of n, so h of n is known as the impulse response, because it is a response of the systems to delta of n. So a times delta of n produces a of h of n, b times delta of n minus 1 produces b of h of n minus 1. So x of n, any signal x of n can be represented as a linear combination of of shifted and scale impulse signals. So then the output of the system is shifted and scale version of the impulse responses. So we talked about one example where x of n and h of n, and then we talked about how we do the convolution for two different types of examples, one for infinite duration and one for finite duration, right? And then next we talked about the properties of the time invariant systems. One is the commutativity property, where x of n convolution with h of n gives is equal to h of n convolved with x of n. This is the commutativity. And then distributivity and associativity property. So these are the systems that we have talked about, properties of the systems. And then next we talked about the memoryless systems and the inverse of an LTI system and causal LTI system. So we gave that if a system is invertible, meaning that the h of n convolved with some other h1 of n, the inverse will produce a delta of n. And then LTI system without memory means that h of n equal to 0 for n not equal to 0. This is the one. And then so this is for inverse, and this is for causality, and this is for stability, which is absolutely summable. So let's take a look at a few assignment questions in the course. So what we're talking about here is, he's asking that if y of n produces x of n convolved with h of n, is y of n minus n naught equal to x of n minus n naught and h of n minus n. How we can go about solving is that we can expand this x of n convolved with h of n, and then expand the second x of n minus 1 naught h of n minus n naught, and see if they are equal. So expansion means that the convolution sum that we're talking here. So several connected in cascade, the order of, if the systems are connected in cascade, the order of interconnection does not matter as far as the overall system impulse response is connected. So we have talked about the properties of LTI systems earlier, so maybe you can use one of those ideas to come up with an answer for this question. And then memoryless system may not be bistable. This again can come from the properties of the systems, right? So yeah, so this is week 3, and then we'll go to week 2 assignment. So yeah, so these are the solutions that we have talked. Yeah, okay, so since so supposed to be a doubt clearing session, and then I didn't students have attended the class, uh, and it's been like 1.5 hours, so I'll end the session here. In the next session, I'll be talking about linear constant coefficient difference equations LCCDE, which is a sub part of LTI systems, and then we'll talk about some syllabus from week 4. Right, so this is what we'll talk in the next lecture. All right. Okay. Thank you. 28. Just wait for 2 minutes so that if anyone joins the class.